Professor, you are so funny, ha ha ha.
Professor, where are you?
Yeah, Lucy, I'm up on the roof. Tell all the kids to come up here. Come up to the roof. We're going to have class on the roof tonight. Wow. Wow. Come on up, class. Come on, everybody sit down. Let's sit down. We're going to do the class in front of the stars tonight. So everybody remember, the waveguide is a metal bar. And I took a copper wire and I wrapped 200 turns around it, and then I stimulated it with sound frequencies in the transducer L1 and L2, and the sound waves bouncing back and forth on the bar, and just to see if we could induce electrical waves into the coil, and mechanical waves all the way up to 20 megahertz induced electrical waves in the coil. No big deal, but what caused it? Well, I'm going to jump up on top, whoa, of the Earth, and the Earth's magnetic field magnetizes the bar. Everything that is ferromagnetic and other elements too get magnetism from the Earth. So if I wiggle it, the coil picks up the movement of the magnetic field of the Earth and induces an electrical current from mechanical wave. Isn't the Milky Way something? Oh man, what a universe. Now we're going to go fast again. I took some sandpaper and took the paint off the bar, and I made a metal spot right there, and I made a metal spot right there, and I connected electrodes or copper wires to the sides of it. And then we're going to stimulate the bar directly with electrical current. And we're going to watch the lag time of electrons as they move down the bar. Well, you know, electrons don't really move down the bar. You put one in here and one falls off the other end. It's kind of like Newton's cradle, you know, bump, 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 bump. But the speed that it crosses the bar is what's really interesting. Now we're also going to show in this segment that electrical waves do the same thing that sound waves do. They go faster as the frequency goes up. And all of physics says, no, that don't happen. But watch, I'm going to prove it. Lucy, take it away.
Just to give a little more information, Professor, here is the steel bar with 200 turns of copper coiled or wrapped around to see the inductive capabilities. Remember, the electrical isolation is high, 50 mega ohm plus. Only mechanical waves are moving in the bar. Here in slide 151 it shows a 500 kHz signal applied to the source piezo L1. L2 is the receiving piezo and C1 is the signal induced in the coil. Since all metalloids are affected by the Earth's magnetic field, mechanically oscillating the metal moves the mass sufficiently to induce a current flow in the coil.
And you can see in this scope shot, we're running a frequency of only 500 kilohertz down the bar. That's because we're not concerned about the delay. You know, the coil causes problems with the frequency and the delay and everything. But that's not what we're looking for. We're only looking to see that the magnetic field moving in the bar induces an electrical current in the coil.
Let's go fast again. We started with radio waves in a waveguide, and then dropped back to take a look at mechanical sound waves, and now we step up again to electrical waves. These are waves that go through a wire. You have 60 cycle waves that come into your house to run all your appliances. AC current was the argument that Thomas Edison and Nikola Tesla separated over, and you may know that the World Columbian Exposition in 1893 presented the Tesla Westinghouse polyphase alternating current electrical power system. Electrical frequencies do not move through a wire at the speed of light, they move considerably slower.
And in this segment, you're going to notice that we added a current probe, because electricity not only has a voltage, it has a volume, which is measured in current, in amperes. Lucy, take it away.
So here we go. The 1 meter steel bar has been modified. There is a bare spot prepared for a clamp to make electrical contact for the insertion of a signal, and the scope probe L1 is attached. On the other end is another bare spot and a clamp with a wire lead attached under the clamp. Around the wire lead is the current probe called a current clamp. This is a special device with an internal coil that you clamp around the wire. The wire lead induces a signal into the coil, and the signal is interpreted at the scope as a voltage representing the current in the lead. Also attached is L2 scope probe and a black lead that goes to a 50 ohm resistor to current limit the test. The function generator again has a 50 ohm protection load resistance. In general, the circuit is mostly resistive, and since all voltages are clamped close to ground with low resistance, there is no radio noise to contend with. There is a small capacitance produced by the metal bar which will show up at higher frequencies, but for the most part the impedance is mostly resistive. Thus with 50 ohms in front and 50 ohms in back of the test location, the source voltage is divided by 2. There are no standing waves because unlike the radio frequency tests and the sound tests there is nothing to reflect the waves back. We begin at 100 kHz. The new current probe is labeled C1 in the slides. The professor set the input voltages so that the waves are separated for clarity, because the only thing we are interested in here is timing. In this first slide 154 you can see that at this frequency, there is no time differentiation. There actually is, but at this resolution and frequency it cannot be seen. If you change the sample function faster, it flattens the graph and all separation disappears. Notice that C1 and L2 are completely uniform. At 500 kHz slide 155, everything looks uniform. The source signal again is external of the bar so to speak, because it is before the clamp. Here in slide 156, we have the first frequency that is at a resolution that you can begin to see the delay. This again is the time it takes for the signal to travel down the 1 meter bar. The frequency is 1 MHz. So, 1 divided by 1 million is 0.000001. It is 1000 nanoseconds or 1 microsecond, but our resolution is too large for an accurate reading. At 2 MHz you can begin to see the capacitance of the bar showing up, by the current leading the voltage. Again, hard to read but, 1 divided by 2 million is 500 nanoseconds and a 15 nanosecond lag would be 1.5 to the minus 8 reciprocated, is 66,666,066 meters per second, since our bar is 1 meter, and it took the current 15 nanoseconds to arrive. At 5 MHz, the current and voltage are considerably separated. Utility companies don't deal with high frequencies, instead they deal with very long wires. In that case most of the disparity between voltage and current is inductance not capacitance, and they add high voltage capacitors to deal with it to keep the voltage and current in phase for the highest wattage output. Anyway, here you can see the lag in time is substantial. At a lag of 12 nanoseconds this puts us at 83,333,333.3 meters per second. Now at 10 MHz we can begin to see some accuracy, and with the current lag of 8 nanoseconds we have 125 million meters per second. While at 15 MHz there is a 7 nanoseconds delay for 142,857,142.857 meters per second. And finally, the professor maxes out the function generator at 20 MHz and we see the smallest lag of about 6.5 nanoseconds for a whopping 153,846,153.8 meters. That is 0.513 or only 51.3% of the speed of light. Once again, please note how, as the frequency went up, also did the propagation velocity, and again it is not the frequency per se, it is the rise time which sets the acceleration. Another very important observation is that this is frequency moving through a medium. Once the electromagnetic radiation moves into the air or more importantly into space or vacuum, it accelerates to light speed. Now this is going to get really interesting, but first is a simple observation before we go on. Question: can an oscillation pass from one media to another and alter its velocity up and down and back up again? This will be very important. The professor thinks with a little demonstration this can be seen without an experiment to prove it. It should be obvious that when passing between different media, sound is changed, but it still passes through, as in this example. Sound moves through the steel fast with broad wavelengths, and slower through the bamboo stick, with narrower wavelengths, and then speeds up again in the next steel bar. The bamboo, though a stiff rod, has more compressibility and flexibility. The waves slow down and become shorter and their velocity slower, and in the steel, they again speed up and stretch out. There would be other changes in amplitude and harmonics as well, and these nuances will be realized in the second steel bar and not in the first. This will be more important at light speed.
Okay, class, we should have a pretty good idea by now that electromagnetic waves, when they change media, they change velocity. They hit the steel bar into a bamboo stick, they slow down, and steel bar, they speed up again, and then when electromagnetic waves leave the steel bar into the atmosphere, they speed up to the speed of light. So as the waves change media, they change velocity and wavelength. Now the physics community is going to probably crucify me, but there is no such thing as the photon. It's dark matter. Now we have Michelson-Morley experiment that tried to talk about the ether, or they wanted to prove that there was an ether or there wasn't an ether. So they set up silver mirrors and partially silver mirrors and prisms, and they crossed beams, and they pretty much proved that there's no such thing as the ether. So what's carrying the waves? So they came up with the idea of the photon, but the photon doesn't exist. And we're going to see that the equation C, which is 1 over the permittivity and the permeability, is actually true, but it all happens in dark matter. Dark matter does the work of the photon, of which there is no such thing. Waves move off from the electron, which is the first order of mass, into dark matter, which carries light waves, just like the photon. So let's take a minute to look at the really complex equation about permittivity and permeability, which gives a value to nothingness, but it's not nothingness, it's really the value of dark matter.
First, Albert Michelson and Edward Morley in the famous Michelson-Morley experiment of 1887, used what they call the Michelson Interferometer. It was a device to send a light beam through a half-silvered mirror and back on itself to attempt to detect the luminiferous ether. Discussed a bit earlier, the ether, after many researchers exhausted every possibility, was abandoned and decided to be wrong. James Clerk Maxwell, who lived from 1831 to 1879, was a Scottish scientist in the field of mathematical physics, who brought forth the complex explanation as to why electromagnetic waves travel through a vacuum, being that there is no ether to carry them. The ability of empty space to carry electromagnetic waves is based on the permittivity of free space or vacuum, epsilon O, and the permeability of free space, micro O, and the speed of light for the equation, C equals 1 divided by the square root of permittivity times permeability. The professor is trying to carry this along, and not overcomplicate this dissertation for the non-professional, and to start arguing equations, so suffice it to say, that all of the work of our prize-winning physicists is not wrong, and it works, but we have more tools now by which to see, and time to clarify. At least in the macro world the physics laws work, because we build stuff, using these laws and it works, like radio and computers and chemistry. We, time and again tweak the values and guess a little better but, well, the professor can't help himself and must elaborate. Permittivity assigns the value of epsilon O, equal to the numbers shown, in farads per meter. This is a capacitive value in farads of empty space. This defines a physical quantity to nothingness. Next, permeability, micro O, equals the numbers shown. This is in henries per meter. This defines an inductive value in magnetic susceptibility in henries, a physical quantity to nothingness, empty space. So, just like the Big Bang that always approaches the ever-elusive zero event moment, somewhere in infinity, if we don't have an answer our best guess will do, and we will wrap it up in some convincing calculus, and call it law. Here is where infinity becomes useful, and it pulls the equations out of nothingness, and says the reason for permeability and permittivity to have Maxwell's values, is because of real matter causing the value observed.
So dark matter resides dimensionally just beyond the electron and evaporates into infinity as we go to the infinitely small, to the infinitely large.
Dark matter resides dimensionally just beyond the electron, and it diminishes into infinity at an infinite frequency, an infinite velocity, and for all of our practical purposes does not exist. Restate that. For all our practical purposes it does not exist yet, that means it does not yet exist in our time frame. It is in the process of coming into our reality, and is so massive, it is the cause of all that you see. The universe did not go bang, in an infinite instant, it is in a continual state of coalescence. It happens infinitely, and it had no beginning. The human problem is that we are finite, and have a beginning, and an end, and therefore the universe must have had a beginning, and will have an end. Wrong, it is, and was, and will always be. You, the temporal observer, is in passing. Yes, but what about the red shift? The universe is in a nutshell, and the nutshell is infinitely large. It is truly relative in all aspects. We will get to this later, but the redshift of light can be explained in skewed dilation, which is what is really happening. To stop thinking in finite terms is difficult but essential. Before this century, the only proof of dark matter is the observance of the cosmic error that occurs, and some observational corrections. So, relax and just take a while to rethink. A light wave can be split infinitely, thus, the laser. Our perception of light is our beautiful spectrum, but, and thus, alpha, beta and gamma wavelengths are just that, wavelengths, oscillations, and not particles.
And this is where we find out that the universe in a nutshell, and the nutshell is infinitely large. The universe was never in a nutshell. And that caused me to retitle the subtitle of the thesis, called The Universe Not in a Nutshell. So now, class, we're going to move from electrical waves into light waves, who I have professed are non-electromagnetic. Alpha, beta, and gamma are not particles, they're wavelengths, wavelengths in dark matter. So Lucy's going to take us now into the realm of the light wave. And I'd like to say that the entry point of the electron is 2.09 to the minus 25, but you know that's just a good guess. The entry point of the electron is probably where the photon takes over. Okay, but it's not a photon, it's waves in dark matter. You know, you just kind of get stuck using the terms that have always come down from the past. But Lucy's going to take us into light waves.
A light wave can be split infinitely, thus, the laser. Our perception of light is our beautiful spectrum, but, and thus, alpha, beta and gamma wavelengths are just that, wavelengths, oscillations, and not particles. Frequencies go infinitely high, but leave our cognizant realm at the dimensionless electron, which you will see has a mass equivalence for our realm. This gives us a good entry point into reality in our realm, and it places the electron, not as a particle alone. It can be a mass, and disappear as a wave. When it is a mass, it interacts directly with matter, in that it produces magnetic fields, moves through conductors, and can be accumulated in atomic mass as weight. Light, on the other hand, does not, and as a result is not particulate. You can switch light on and off, and you can produce light with many devices, but you cannot modulate its frequency. Light once produced by a device is past tense in time. Electrons can be modulated after emission, and can be bent by magnetic fields, light cannot. Thus, we are stuck with divisive methods to determine its frequency. We have no light frequency oscilloscope. All we have is diffraction and calculus. How fortunate we are to have those tools. The value of 299,792,458 meters per second is a good starting point for the speed of light. Empirical test cannot produce this perfect of a result. This value is derived from the amalgam of work done by Newton, Voltaire, Ohm, Watt, Ampere, Coulomb, Henry, Faraday, Gauss, Lorentz, Maxwell, Heaviside, Planck, or Einstein. Let's just say it was a collaborative effort. The velocity is more or less a process of elimination, but yet, let's just say it is a good place to start.
Class, I had to read this one because I couldn't remember all the names. We got Newton, Voltaire, Ohm, Watt, Ampere, Coulomb, Henry, Faraday, Gauss, Lorentz, Maxwell, Heaviside, Planck, Bohr, and Einstein. All these guys worked on the velocity of light, trying to nail it down and lock it into a specific speed. And now we come down to this value, 299,792,458 meters per second. Now it's in there somewhere, and I think it's somewhere around green light actually moves that speed. But the interesting thing is, they say that it's the phase velocity that causes things to diffract, which is totally wrong. It's the velocity of the light that causes it to diffract through a prism, and we're going to see why.
Here is the issue the professor will defend. If all the frequencies of light traveled at the same velocity, they would not diffract. Velocity of all waves is dependent on the media and frequency. As has been shown with mechanical sound waves and electrical conduction waves, the rise time of the wave sets the velocity. The variance is large with low frequencies, and diminishes as the frequency increases. The professor will show that the decrease in velocity variance is exponentially smaller as the frequency rises, and that the propagation difference is positive. As frequency goes up, so does propagation, and that in all media denser than a vacuum, electromagnetic propagation is slower. Now that is, electromagnetic waves slow down when encountering media other than air or vacuum, and vice versa. Mechanical waves propagate faster in media that is denser than air, and sound waves do not pass through a vacuum.
Now, one of the mistakes that's been made in most diagrams of the light going through a prism is they show it coming into the wall and it starts the diffraction, but that's not true. It comes into the first wall, it goes straight across as it slows down, light slows down in the prism, and then when it gets to the back wall, it spreads out. That's where the diffraction happens.
The diffraction of light waves only occurs on the exit from a media transition. That is, they do not diffract or separate when they enter a media, they only change angle. The diffraction or separation of colors occurs on the transition from a media to the air or into a vacuum. Drawings that show the separation in the entry of, and while passing through a prism, is in error. There is an acutely sharp point of emission. The beam that crossed the prism was razor thin on entry. The angle of the light bent, but remained narrow and white, until emission and then diffracted. So, let's look closely at diffraction. The next slides were months in the making. The laser has a beam that is 0.9 mm in diameter, and it is round. The spot it projects on the surface of the prism is stretched to an ellipse, and it is now 2 mm in height and 0.9 mm in width. The beam that crosses the prism maintains these dimensions, and the exit ellipse is likewise the same as the entry ellipse. Let's return to interference patterns for a moment for a closer look.
Now this one is really important. It's impossible to make a slit thin enough that it doesn't refract or reflect the light. Light, because it's infinitely small, can be divided again and again and again and again. You can't make a physical obstruction that is thin enough that it doesn't cause an angular deflection of the light.
To restate, it is physically impossible to make a slit that is thin enough to not reflect light at some angle as it passes through. Even steel or any element becomes transparent and affects the transmission angle as it interacts with the atoms. But more important are the physical characteristics of the wave itself. So, let's get away from the wavelength and consider if we have only one. That is one wavelet. It will still behave just as if we had successive waves that establishes a wavelength. A wavelet by itself is a compression wave in that it has a beginning, an amplitude, and an end.
And, you know, it's so difficult to get people to understand or to accept, it's just observations, okay? But light waves are flat. Now I know, there's no such thing as a straight line. But nonetheless, any angle or perspective that you get on a light wave, it's always coming at you flat. It doesn't have any curvature. And when it's split, it goes straight until it hits something to make it curve. But I can divide it and divide it and divide it, and it's always flat and thinner and flat and thinner and flat. That's why we got lasers.
To refresh your memory, light waves are flat, and not like the curvy graph representing the velocity, compression, and duration of the wavelet. One wavelet will reflect and diffract all by itself, independent of any other wave, and from the time the wavelet abruptly stops, and until the next wave starts, is zero energy. Thus, there is no correlation to reflection, and diffraction, and wavelength. Furthermore, light waves are not like waves in water that expand and curve as they pass through a slit. They are flat, and the interference pattern is a function of time and not angle. The interference pattern is established immediately upon the exit from the slit, and is persistent at any distance at any angle, which refutes the curved wave theory. Just any picture will do, but it is a matter of integrity. On the bottom of slide 169 you will notice the interference pattern is compressed on the right, and expanded on the left. The top of this slide you will find all the patterns are uniform. The camera does not like laser light, and has a difficult time focusing. So, what is a light wave? We will talk about just one. It is a compression. Matter when hit with this wave is moved by the energy. It is not moved forward, and it is not moved backward. The matter receives the wave and it swells, differentially. Here is a light wave entering water. The wave is huge compared to the size of a water molecule, and as all energy waves do, it wiggles the molecules against each other, adding energy. Non-coherent light bounces in all directions and can be seen in any direction with infinite reflections. Make the light bright enough in amplitude and it will boil the water into a gas. This is one wavelet. Its duration is 0.7755365 femtoseconds.
And then, as I said so many times before, that a wavelet all by itself will diffract. It doesn't need a phase velocity or any relationship to any other wave. A single wavelet all by itself, you might want to call it a pulse, will still diffract. So it doesn't have any relationship to any other wave or phase velocity.
It has no family or brothers and sisters or cousins. It has no relationship to anyone, and there are no waves before it, and there are no waves after it, yet it will reflect and diffract by specific laws not related to wavelength, but specifically by its own properties. You can increase the amplitude, which raises the energy level, but if you alter its duration, that alters its propagation velocity, which is how rapidly it went from 0 to light speed, and abruptly stopped. This alters its relation to matter, and more importantly its relationship with space and time. Not to be confused with space-time.
Well, class, we ran a little bit long in this segment, so we're going to have to roll over into episode 8, where we actually see why light bends through a prism, and how it's not phase velocity, but it's actually the propagation velocity of each different color. And I sure wish you students would talk to those guys over at NASA. You know, they're measuring the universe all wrong. We could get it right. Say, Lucy, do you want to dance?
Sure, Professor, let's dance. Ha ha ha, ching-a-ling.